Some of the class. How are you doing today? Any questions on the previous lectures? Homeworks, assignments, labs? Anything that was unclear on the previous lecture? We continue the previous lecture, so if you have any questions regarding the previous part, it's at all. To remind you, we talked about areas, lenses, volumes, and then we generalized determinant as representative for all of the above. And we got also to all of the formulas that we had. Lecture, where we got to all of these formulas, the basic formulas for building multiple different things. And we talked about determinants, how to compute nth order determinant. And when I'm talking about that kind of examples, and when I'm talking about numerical computations by hand, it's just practically to brush up your material on linear algebra, because this is not even numerical analysis yet. We haven't got to real thing yet. These are just things to remind you where all the things are coming from. And more or less motivation, you will not need to compute things by hand, really. Computers can do determinants easily. One command method, you're doing that, compute determinant, whatever order. The thing is that you need to understand where the things are coming from for motivation for other things that we are using numerical methods to. Because again, I explained already that determinants of higher order are very difficult to compute directly using the recursive rules that we learn here. And I'm just showing you like why that is cumbersome, why it's difficult to do that by hand or even by computer when you have higher order determinants. And sometimes you have matrices which are like 1 million by 1 million elements. So clearly, if you want determinant or inverse of that matrix, you would not go through determinants, reducing every time by one the order and get like 99999 number of matrices to compute again, just to go one order. Like it's infeasible to do that. Okay, so you have other methods, numerical methods for that. So we discussed rules of the determinants, which are again basic linear algebra, but sometimes we're using these rules, so I want to mention them. And many things in that course as graduate course. This is, in my opinion, difference between graduate courses and undergraduate courses. In undergraduate courses, you are learning techniques mainly, how to compute something, or how to answer questions correctly based on whatever input you have. In graduate courses, it's more like an overview what is available, and you will figure it out when you need it. Okay, you just need to be aware that this is available. So this is what you need really to remember, that these things are available. You have different kind of rules for determinants. These rules will help you to simplify different things. If you need to solve some matrix equations or whatever you need to solve in your actual project or whatever you need to do. Okay, so this is the idea. You will just be aware what is available, and this is why I'm not getting too much into numerical examples, how to compute it. It's more like basic linear algebra. You can go to any textbook and find examples how to actually compute it by hand or even with a computer, right? So this is not the point of the things. The point is, and this is why I'm kind of jumping fast from topic to topic, just to overview what is available. And we are not covering even probably like 20% of linear algebra. Okay, we're jumping just through all of these topics. So we talked about how to solve linear system equations. And all of the things I'm, again, giving you because I will be using that as example for all kind of other numerical things. So if you need to solve system 2 by 2, I don't want you to go through elimination, like Gaussian elimination, which is a long way to go. I just want you to do that. Okay, very short, one-liner for solving everything. All right, so we got back to the areas, lenses, and we defined that as points. So I want, like, we haven't seen that very well previous lecture, so I enabled the annotations, which are that blue thing. So I just want to provide some definition here because we will be using that in today's lecture, right? So I will define that type of determinant as determinant based on 2 points, P1 and P2. If you remember, P1 and P2 was, see what it was. So this was like P1 and P2, P1, 2, 3, going counterclockwise. This is P1, 2, 3, 4, and so on. Okay, so you're going always in the positive trigonometric direction, which is against the clock. Okay. So this is how I want to define that type of determinant. So 1 divided by 1 factorial, which is still 1, is that x1 times 1 minus x2 times 2, which is length of the interval between P1 and P2. So I will write that length as P1, P2 pair. Okay, so remember that each one of them is a vector. But this is for simplicity of notations that I will have just 2 points, and that determinant will tell you the distance between these 2 points. Okay, this is the length. For 3 things, I will define that as P1, P2, P3. So it's triangle area in a sense, and this will be defined as 1 divided by 2 factorial and that type of determinant that we discussed previous time. Okay, so this will be all this P1, P2, and P3 points. This is my new notation. And this is P1, P2, P3, P4 for 3-dimensional shapes. And I will explain in a second why it's important for me to write it in such a compact way, all of these vectors, just stacking them together in the same brackets. This is a summary of all of these definitions, okay? We will be working mainly with that definition because I will give example how to compute area of any polygon using only determinants. And also how to measure areas of any curve inside the curve, any curves that you want, which is typically done by integrals, right? You need like some curve integral to compute lengths of the curves, or some area integrals, which are 2-dimensional integrals to compute areas within some bounded region, which is kind of complicated, especially if the function itself is complicated if you compute integral, but you don't need to. If you have some sort of grid and your points are particular grid, which are numerical points, and typically in computers you have only that kind of representation of functions, which is digital representation, then you can compute it very simply by determinants. This is what will be the area that we are defining here. And obviously you can generalize it to any number of dimensions. So you can have hypervolume definition, which is just using bigger determinants, but we will be using that determinant as example, okay, for computing areas. You can describe also volumes by triangulation of the space using these pyramids. Yes.
And does the direction really matter?
Yes. So this will be positive direction, which is this definition. So previous definitions, you will get positive areas. If direction is opposite, which is clockwise, these numbers will be negative. Okay? And the area technically could be negative, and we will use negative areas for a particular cause, just for formula's sake, for convenience, in a sense. But as we understand areas, like physical area, it will be only positive. Right? So you technically need absolute value of that value to show if you want to ignore the direction. Okay? So direction will change the sign of the area. That way it's positive, that way is negative. Same thing in trigonometry, right? It's like this is positive direction, this is negative direction of the angles. Yes.
And my second question is, you only have 2 points, and then you connect them. We know that we can get just the length, the distances. But, if it becomes a triangle, we have the area and then the perimeter. So, and then if it becomes a solid figure, volume function. So when you apply the determinant, which kind of guideline will it tell you whether this is volume?
So the first one is length. First one, the top one here is length. Second one is area. Third one is volume. Okay. So if you need pairwise distances of each side of the triangle or any polygon, you have P1 and P2, and P2, P3. So you connect them pairwise, you say like P1 is connected to P2. I want length of that thing. So computing the closed determinant where you have those x1 and x2, right? So you're connecting as a length. So you can compute the linear distance between the pairs, adding them together, the length of the perimeter, the shape, whatever the shape is, triangle, whatever. With straight segments connected to this point. For area of that thing, and we are talking here only about triangles, okay? So the area of triangle points P1, P2, P3 will be the second determinant. And the volume of the pyramid specifically, not any other shape, just the pyramid is 4 points. Tetrahedron, mathematically, name for pyramid. Then you have the third volume determinant, right? And you can extend it to also kind of hypertriangular shapes in more dimensions, and then you will compute hypervolume of the things if you need to segment the space into those hypertriangular shapes. Because what people typically do, they triangulate the space. So any shape would be divided into triangles, right? And the shape, overall shape will be like just built from triangles, covering that entire shape. And the idea is that you can compute areas of these volumes just by taking all the triangles inside the shape, instead of computing that integral, which is computationally complicated on a curve. Okay, it's possible. You don't have to use it for area, but triangulation is also useful for all kinds of other things. Like in modeling, you use a lot of triangulations for mesh shifts or movements. Let's say you have some body which is moving and deforming. So how these triangles are deforming, showing you all kinds of stretches of tissue. It's used mainly in mechanics, but you have also other areas where you have a lot of triangulations that people are doing. FEM methods are all that kind of approaches. But we are not talking about that in this course. This is also my expertise, and a lot of people there. But it's like practically used almost everywhere. Triangulations of different things, or in space, you are doing those pyramids bind together into some bigger volumes, particular shapes, approximating shapes. All right, so it's easier to compute on triangles. All right, so the geometric meaning of determinant is very simple. Determinant of regular shape is just 2 by 2 would be area of that parallelogram. Okay, so this is the area, the pink thing. If you have points C, D, and AB, the determinant of A, B, C, D is AD minus BC, and this is the area of that parallelogram. And for 3 by 3, like 3-dimensional shape, it would be area of that, whatever that shape is called, parallelepiped or whatever it's called. Do you remember the name of that shape? You have some name for it, but it doesn't matter. All of the sides are parallel, okay? But it's not, it's slanted, rectangular type of shape, 3-dimensional. So the volume inside of that is practically 3-dimensional, based on like points R1, R2, and R3. All these vectors which are building that kind of thing, these 3 vectors. So coordinates, if you put them as columns in your determinant, this determinant will give you volume inside of that blue shape. Okay, this is geometric meaning of determinant in general. And this is why if you take like 1/2 of that, you'll get the triangle. Okay, and if you take like 1/6 of that type of shape, you get kind of cut of that parallelepiped shape, right? So as I mentioned already, sign of the determinant means in which direction you transverse all of the corners. If you're going clockwise, you get positive. If you're going against clockwise, you get something negative. And this type of computations are used frequently in physics. I don't know if you're using a lot of physics, but if you go to mechanics, this formula is extremely popular. So it's cross product and dot product. And also in the electromagnetic fields, you have that kind of formulas in Maxwell equations, that same type of things that you need to compute. And this is also determinant. Okay, so determinant is computing these 3 things on vectors in three-dimensional space. Okay, it's I believe it's right-hand rule, where you have magnetic fields and electrical fields perpendicular to each other, and then you need to multiply them that way to get some force, something of that kind. Like a long time ago, I don't remember all of the electromagnetics anymore, but you might use it for something. And then the question becomes why, regardless of where your points are, if you're going clockwise, it's negative, but counterclockwise is positive. And we are talking about determinants of the shape where you have vector, vector, and ones, right? Column of ones. This is how determinant looks like. So you have first one is your first coordinate of the first vector, building the triangle. Second coordinate of the vector, which is like P2 point, okay, in 3 dimensions or 2 dimensions. And then you have vector of ones. So what happens is that you can prove it relatively easily. The idea is very simple. I'm not showing the full proof, but I'm showing just the idea why that direction is always positive. So we start with a very simple triangle. And this triangle is built on vector 1, 0, and 0, 1. So this is right triangle, clearly, right? And if you're computing area of that triangle, okay, using the formula that we used in that direction, so it will be P1, P2, P3 in positive direction, trigonometrically positive direction. You will get 1/2, then 1, 0, 0, 1. In short, it will be something positive, okay? So the area of that thing will be positive. Now, what do you need to do? How do you need to move the points in such a way that it will change the sign? So you're moving continuously these points in space, any way you want to any point you want. Okay, so each one of them will have one of these black trajectories, whatever they are. Okay, so you're moving all of these points. Like imagine that you're taking each corner of the triangle and you're transforming it in any other triangle you want. You can do that, right? And you're just moving it in space continuously. Each point moves to the new location of new triangle, wherever it is. Okay, so you get clearly 3 different vectors, 3 different points. So instead of origin P1 and P2, you get some other points somewhere in space. But you are doing that continuously, right? So these vectors will change. This vector will stay the same. But these vectors will change continuously, which means it will not jump somehow from one set to completely different set. So these numbers, like each element in this vector, will change continuously, slowly. It will not jump. It will not have any discontinuities in the trajectory of each element in that matrix, okay? Which means that the computed value, which is some sort of combination of these numbers multiplied by each other, is also changing continuously. So the determinant is also changing continuously somehow. So what is the condition on the determinant that it will change the sign?
How are you? I mean,
To get from positive to negative, you need to cross some number. What would be that number?
which 2 column?
I don't know. You're not switching anything. Everything is changing continuously. You're changing, but little bit. Like every single number moving on a trajectory. Okay, this is going up, down, wherever you want it to go, but it's not jumping. You don't have any discontinuities, and you don't have any discontinuities in determinant. And the claim is, what should happen? Not claim, question. What should happen to the determinant while it's passing from positive to negative? It should become 0 at some point. Okay, so for a particular move, if your claim is that you walked that direction and you moved all of these points, eventually something needs to happen to the determinant that will become negative, okay, to these points. Like you're saying that for a particular location of the points, it will become negative. So what is that location where it's kind of threshold? This is where determinant is 0, because determinant is changing. It's still positive, positive, positive. You're moving the points. And then suddenly it cannot jump to negative without passing through 0. So it has to pass through 0. So what is that location of points where determinant of that kind of thing of 0.1, 0.2, and 1s will become 0? What the points should be? What is the conditional points now for the determinant to be 0? They will become collinear on the same line, okay, proportional to each other, practically speaking. Okay, they will become linear combination of each other, which is 2 points are sitting on the same straight line, which means that to pass from positive to negative, you actually need all of the lines to become straight line, because if all 3 points sitting on the same line, it's not triangle anymore, right? It's straight segment with 3 points on it, okay? And this is a condition where it becomes negative. So you had that triangle, okay? So you need to move it like that until it becomes a line. And only then when you switch in the direction, the middle point, okay? Obviously, the orientation will be going in that direction now, when you kind of moving from that direction to that direction, crossing that like straight line. This is where it will become negative. So if you are preserving that location and you're not passing through that line, you're not generating any kind of other direction, your area always will be positive for any triangle. Okay, this is kind of idea of the proof. So no matter how you move, as far as you are not getting to straight line, you still keep same orientation, and then you also keep same positive area. Where you cannot get negative unless you switch in the direction. All right? Any questions on that?
But can't you move 1 point? So when you move that 1 point, this is counterclockwise. Let's say you have 2 points on the line and a third point. Can't you move that 1 point counterclockwise to this side?
But okay, you can, sure. You have those 2 points and you have that point. And this point is moving here. By the time when they will be on the same, you cannot do that without having all of 3 of them on the same line.
And then,
so this point will be, at some point it will be here, same line, right?
That's
and then you changing the direction then. When you're crossing that line to that side, like as far as it is on that side, you still have same direction, right? Same orientation. The moment you on that line, you have no orientation practically, but it's a straight line, it's not triangle. But the moment you cross that side, you change the orientation, right? Because now the triangle will go that way instead of going that way, right? So that's the same thing. So you have to pass through straight line segment, then the determinant will change the sign. And when you pass in the straight line segment, then points change orientation. The order of points changes. Okay, this is a condition. Okay, any other questions? Yes.
Give an example to show the process.
Here's the process. Like you're moving from points P1 to 3 to the points which are, this is your new points. Okay, the end point, and end points. You have that triangle now. Triangle like that. Okay, between these 3 points. So this new triangle, since you moved and haven't crossed the straight line, will have the same orientation and also positive area as any other triangle with the same orientation. It always will be positive. As far as you are not, again, squeezing them to straight line. And then it will change orientation and change the sign of the determinant. This is the overall idea. Again, this is not formal proof for anything, it's just how the actual proof goes. And now we are moving to triangulation, which is very interesting formula for computing any kind of areas for any kind of shapes. But we will start with polygons. Let's say we have triangle first, and we will add to that point P0 somewhere in the middle, okay? So each triangle could be sub-triangulated, which means I can divide it into 3 different triangles just by connecting to that middle point from each corner here. So I had points P1 to 3, now I have that P0, whatever that point is, okay? Kind of origin point. And this origin doesn't have to be 0, 0, it could be any point, really. So I'm picking one point inside of the triangle. And I'm saying, well, I will define each one of them in positive trigonometric direction, okay? And I will transverse all of these points, and I will compute area of the entire triangle using that formula. So area of P1, P2, P3, which is P1, P2, P3, the entire triangle. Like try to follow what I'm pointing on the screen, okay? So the overall area of that triangle is P1, P2, P3, right? And absolute value of that, because I want positive area, equals P0, P2, P3. So it's P0, P2, P3. So this is area of that triangle, all right? Plus area of P0, P3, P1. P0, P3, P1 is that triangle. And plus P0, P1, P2, that triangle. All in positive direction. So sum of overall triangle is sum of these three triangles. Obvious, right? So far. Now, the claim is that obviously without absolute values, it also will work. Why? Because each one of them is positive. So absolute value of positive number is positive number. I can remove the determinant, the absolute value here. This is not determinant, it's absolute value. All right, and that's why I'm using that notation. Just if you remember, I defined this as these areas, just for convenience that you'll be able to write that type of formula. So this works without any problem on any triangle, practically, okay? If you go in that direction. Now, what happens if you P0 point outside of that triangle? Like that. So you have still same triangle, like P1, P2, P3, but I'm putting that point outside, somewhere else, not inside the triangle. So let's see what happens. It's a little bit messy here, but let's try to follow. So you want to compute area of that triangle. So what is the area of that triangle? Let's see if this works with this one, with the same formula, okay? So this is area of P1, P2, and P3. This is what I want to find, okay? P0, P2, P3, P0, P2, P3. So this is that triangle. So this is area of that triangle, all right? P0, P3, P1, P0, P3, P1, it's plus area of that triangle. So you're clearly already getting area higher, like bigger than the area of the original thing, because I'm adding the area of that triangle now, extra area, okay? But then I'm saying plus P0, P1, P2, P0, P1, P2. Pay attention that the order of points is negative, which is clockwise, right? Which means that that area will be negative area. So I'm practically subtracting that area. So I said, this is that triangle plus that triangle minus that triangle. And this is the exact area that I wanted in the first place, because I just removed the overlap that you had outside. So practically this formula, if you assuming that areas could be positive and negative, could work for any point P, no matter where you put it. So P might be like arbitrary point anywhere in space, okay? And then you can compute area of the triangle with any point P0, wherever you choose it. Okay, so you can divide it into these three triangles. And this is just a reminder how the area is computed using determinant, okay, for each pairs of points. Any questions on that? So we developed some sort of formula, which is helpful for dividing triangles to subtriangles, which is probably not very interesting because we have formula for the entire triangle. So we can use just that formula and get the answer instead of summing three formulas and getting the same answer. Okay, not very interesting. But what we actually want to do is that this proof of the formula is to compute areas of that kind of thing, which is polygon of some kind, all right? And we can connect it from triangles given some point P0, which is arbitrary point inside or outside. It doesn't matter, it will not matter for us. But before that, like just to see formal proof of that, like why this formula works always, there is a trick how to do that. So using 4x4 determinant, and you're computing that 4x4 determinant using just regular computation. And since two columns in the determinant are dependent, the determinant by definition is zero. So you have two same columns. Like you have two columns of the same kind, it's always zero for determinant if you have two proportional columns all right? So this determinant is by definition 0, but I can develop it by the one of the columns, okay? Let's say last column. So I'm developing by last columns, I get 4 determinants, then I'm practically writing definition of each determinant that I know from this formula, okay? Cancel multiple different things, and then practically I get that formula. Again, you don't need to know that proof. It's just the idea how people are doing different kind of tricks with determinants to prove different things. Not very interesting in that course. Okay, yes.
Question about, is this direction, is it dependent on where you look at it, or is totally dependent? How to
Direction of what?
direction of counterclockwise or clockwise?
So clockwise will give you negative areas, counterclockwise will give you positive areas.
I mean, how determine the clockwise or counterclockwise? How you determine?
Clockwise is the direction of clock, that direction. What do you mean?
Is it depends on where you look at it, the angle you look at it, or the way?
No, you have triangle, right? Shape. So if you're going that point, that point, that point, or that point, that point, that point, but in that direction it's negative. So it's like with clock, as like regular mechanical clock. Okay. If you go in that direction, which is positive trigonometric direction, then you go in that point, that point, that point, or that point, that point. It doesn't matter with which point you start. That doesn't matter. But in which direction you go, you're going against the clock. Okay, then it's positive. It's positive trigonometric directions, counterclockwise direction. Okay, so all of these directions, as I'm drawing them here, are counterclockwise. Okay, this is not how the minutes and hours go on the clock. This is against the direction of the clock. Okay, it's going that way instead of going that way. Okay, so you can generalize that same formula for any number of triangles, which means you're saying that if you have some sort of polygon P1, P2, P3, all of these points, okay, and they are in order, like P1, P2, P3, P4, P5, and could be convex or concave, whatever, any polygon, any bunch of points, right? And then the point P0 will be somewhere. It doesn't matter even where. Okay, you just pick any point you want. The overall area of that polygon, which means all of that area inside, assuming that you're going in the positive direction for each triangle, will be sum of these triangles, which is also kind of obvious. You can divide it as many triangles as you want, depends on number of points. So more points you have, more triangles you will have, right? But sum of that shape, some of the areas will be sum of these triangles. Has to be, okay? So you can write that as that formula. So you're taking P0, P1, P2, P0, P2, P3, P0, P3, P4, P0, P4, P5, and so on. All of these triangles. So you're adding all of these areas, you get overall area of that polygon. And each one of this will be like that. And coordinates of these points are given to you. So you're starting with coordinates of these points, okay? Coordinates of x0, x1, x2, which are your x's, and then all of the y's, like xy coordinates of each one of these 3 points, okay, in each row, and then vector of ones, and then you compute the determinant, you get each one of these components, you can compute that kind of area. Any questions on that? So this is how you compute areas of polygons. Now, how you compute area of any closed curve, whatever that curve is. This is even more interesting question, but you're doing that exactly the same way. But you're dividing that into infinitesimal triangles, like really tiny triangles. That's how it goes. Again, you pick some point P0, and this point could be anywhere, like wherever you decided. It could be like 0 point, the easiest one for computation. But you can choose it somewhere, okay? And then you're saying, oh, I have that curve described by discrete points. So I have like point 1, 2, 3, 4, 5. It's like your boundary of your curve, whatever it is. And you have coordinates for each one of these pixels in the image or whatever that thing is you're describing, okay? Now, you can compute that as P1, P2, P3, P4 on the boundary, like one by one, right? So what happens is your Pi will be Xi and Yi, which are coordinates of that point on the boundary. And then that vector here will be, I will call it delta P, which is like tiny little thing. And these are those differences between this point to the next point. It's like vector which is pointing to the next point. So you'll be able to compute them like that. So the coordinates will be Xi and dxi for your next point in that same triangle, okay? So area of that infinitesimal triangle, which is shaded area here, will be 1/2 as usual, 0, which you start just with 0, 0 point, okay, origin point, whatever, for simplicity. But it could be any other point, so it doesn't matter really. X and x plus dx, like plus the small vector, which you computed to the next point, all right? And this is the same thing for y. Y plus dy. This is the point yi plus little delta to the next point, right? And then vector of ones. So if you compute the determinant, this is what you get, that type of thing. Now you need to sum all of them together for each I. So it's like sigma on all of the things with xi and dyi and yi, dxi, and 1/2 would get out of the parentheses of the sigma because it's linear operator. So it's 1/2 of the sigma from 1 to whatever number of points you have, and then all of these elements. Now, if you go to infinitesimal sigma, this is integral. Okay, it's like infinite number of elements in the sum. Now, do you know what S stands for? The integral symbol. What is integral symbol? Meaning of integral? It's like, it's from sum, practically. The original idea of integral was just infinitesimal sum. So it's like long S in a way. So symbol of integral is just long S. This was the idea. You're just summing infinite number of elements. So it's sigma with infinite number of elements, practically speaking. Okay, so this is integral. And this formula is known for integral on that curve to get area. Okay, this is exactly how you compute area of closed curves in integrals, okay? So we developed that formula just from linear algebra, and you don't have to use it. You can use sigma on that thing. So you can put 1/2 sigma on whatever number of points, and here you approximate it with xi and dyi. Okay, everyone will have index I for each point. And you do just same computation for finite number of points to approximate the area. So here's a formula, which is generic formula for any closed curve. And you can compute area of closed curves, which is very interesting computation. And I want to finish that lecture with one interesting theorem, which was developed by George Peck. So he was a very interesting figure. He was Austrian mathematician, unfortunately died in German concentration camp in Second World War. And he developed very interesting idea, which is not really generalizable. I looked for maybe some people developed something new for more dimensions, but this works only for 2 dimensions. And if you have some shape on the grid, okay, let's say you have some grid, and your points are only integer points on the grid. So grid is like 1, 2, 3, 4, 5. In that direction, 1, 2, 3, 4, 5. In that direction, so you have those squares, okay, like image. And then you have particular pixels or particular coordinates where you have boundary of the shape on that grid, on that lattice, right? So how can you compute area without counting the actual area inside? Which means just based on the integer points, because areas like exact area, not just number of pixels inside of the area, because like number of pixels inside, here will be all of the green points or plus red points, practically this kind of area inside. But this approximation, because these lines cut pixels, like each square is single pixel, single element, picture element, okay? But this is crossing through them So some of that is like fraction of that square. Some others are bigger fraction of that square. Sometimes it could be full square included. Like how you compute the area of that thing, right? It's sounds like very complicated problem. Like you need all of the coordinates and you need all of this like smaller areas to compute them separately. Number of squares, full squares, you compute in separately. And then you adding them together somehow, all of these fractional parts plus full parts. But he developed very interesting theory, which is stating very interesting thing. Just count the number of points inside, count the number of points on the boundary, divide them by 2, and subtract 1. And this is the area. This is actual precise area of that shape. Okay, whatever that shape is. Okay, you count in the number of points on the boundary, on the integer grid. So all of them will be integer numbers. Okay, you'll have particular integer number of points on the grid, on the boundary. You count in what are the points which are inside the shape, which are red points. You add half of the boundary plus inside minus 1, you get the area, which is very interesting and simple formula. So in that example, you have 7 red points, 8 green points. So it will be practically 7 plus 4 minus 1, which is area of 10. The shape has exact area of 10. Very interesting theorem. Very useful for computations and computer vision, where you need to find exact areas of particular shapes, especially in writing games, when you need particular interactions between different shapes when you're writing graphics. So you're using that type of approaches, which gives you like extremely simple formula. You don't need any square roots. You don't need super simple. Count the points inside, count the points on the boundary, and you get it. All right? Any questions?
So you were saying you haven't seen this, to your knowledge, being extended to higher number dimensions?
Yes, I hope to find that in 3 dimensions at least. Some kind of simple formula counting voxels inside, voxels on the surface, and then doing with them some formula, and you get the volume. No, couldn't find anything like that.
Prove this theorem?
Yes, there are many proofs actually of the theorem. It's typically based on the topological theorems of Euler related to number of triangulations of space. So it's based on triangulations in general. I don't remember the proof, of course, but I'm sure you can find it online. That kind of theorem. It's not too complicated, but it's related to topology, topological parsing of the space. Yeah, I don't remember details. Any other questions? Okay, some examples of practical applications of distances. And if you find some other examples, I'm happy to provide other examples, but I'm picking things from my own work and expertise. So sorry about particular direction of the examples, because my expertise is mainly in control systems, signal analysis, computer vision, and machine learning. So most of my examples are coming from these areas, but I'm sure it's applicable to millions of other areas as well. Okay, so if you have some different area to apply it to, you practically can do exactly the same thing and get it for your type of data, whatever you need to analyze. And again, I don't really know what you need to analyze. So this is coming from our project on neuroengineering. And in that project, we have multiple signals recorded from the electrode inside the brain, which means it's intracranial IEG, intracranial electroencephalography. So it's not that cap that you put on the head, which is typically people use for all kind of brain-computer interfaces, EEG cap, measuring EEG. We are measuring that from inside the brain. So electrodes are implanted in the brain during surgery, of course. And then we record all of the signals from inside of the brain. And this kind of signals from STN subthalamic nucleus, recorded on directional electrode in Parkinson's patients where they are installed DBS, brain stimulator, to stop tremors and other bad things which are happening in Parkinson's. So this is practically kind of last line of defense after medications stop working with Parkinson's. And as you might know, Parkinson's is progressive disease, which means you cannot really heal it in any way. So people die with it eventually. But they can live many, many years, sometimes like 30 years or more, with Parkinson's. And we know probably most famous actor is Michael J. Fox, who has Parkinson from pretty early age. He got it when he was 30 something, and he got surgeries and nothing helped. But he's still alive as far as I know. And he's doing okay with all of these devices and medications that he's taking. Of course, he has a lot of problems with tremors and other things, but dystonias, walking, speaking, Parkinson has lots of different real problems. And people know Parkinson only for tremors, like hand tremors. Hand tremor is like almost, you can almost ignore it compared to all other bad things which are happening to Parkinson's patients, because like just imagine that you could be paralyzed for a second and you cannot control your body for a few seconds, and then you can fall on your face or on your back and hit your head. That happens all the time to Parkinson's patients. So tremor is like a small thing. It's not convenient, it's difficult to drink and difficult to do all kind of other things that people typically do and do not think about that at all. But there are much worse things happening in Parkinson's, okay? So this deep brain stimulator helping them, and we tune in the deep brain stimulator to stop tremors and other bad things which are happening to them, and they can live longer life and better quality of life with the deep brain stimulator. So these are the signals that are recorded from there, and one of the typical questions that people ask, how similar they are between different channels. So recorded in multiple different places in the brain. You want to say like, well, how each one of them communicate to other part of the brain. Like how connected they are, connectivity type of studies, how different parts of the brain communicate and connect to each other, okay? So you have a lot of different studies in neuroengineering related to the connectivity question. And connectivity you can detect by how close signals from different places are. But what is close? You need some sort of definition for distance, that the distance between them is small. But again, what is small? You need to define what is small, right? And you can think about correlations between different signals. You can think about distances between, like Euclidean distance as example. But Euclidean distance, for example, is not normalized, which means it could be any number, right? It could be from 0 to infinity, Euclidean distance. But you want something which may be between -1 and 1, like correlation, like Pearson correlation coefficient of some kind. So you have all kinds of types of distances which are describing that normalization of different kinds. And we discussed already multiple different distances. So I just want to show you some examples how you find pairwise distances between multiple different channels and how they look like and how we can interpret that and to give it some meaning, all right? So let's say you have this 10 channels recorded from the brain. They could be from surface of the brain or from inside the brain. It doesn't matter for that particular exercise. But you have these 10 channels. I just plotted them all together in the same system of coordinates. No filtering, no nothing. This is how raw signal would look like. A lot of noise, as you can imagine. Okay, brain signals are microvolts, which are like super tiny signals. Recording them is very difficult. You don't have ground, which means all of them are floating on absolutely virtual ground. So you cannot connect patient to the main power, okay? Not safe. So they are all insulated from the mains power, obviously. So you have ground, which typically they measure here on the, like behind the ear, or somewhere in the middle here, or average between 2 ears, like mastoids, they put it on mastoids. You have all kinds of ways to define zero, which is ground. In electrical engineering, we typically do not have that problem because you're just using Z0, which is actual ground. On the body, you cannot use that. So it's all floating. And you have also DC drift, which is typical phenomenon where signals just go on DC bias, which is artifact of the recording device because you don't have any ground to measure zero. You don't have zero. Zero is floating and could be anything. And could be also noisy. So you get horrible SNR, signal to noise ratio, and you get that type of signals which all look like pretty much pure noise. And you need to extract some information out of it, like how similar they are, how close they are to each other, how to filter them, and all these questions. Okay. So in MATLAB, to use pairwise distances, you have a function which is called pdist, pair distances. All right. And pdist takes two components. The first component is that matrix X, which would be all of the 10 channels given as columns. All right. And then you will have practically 10 of them as a matrix. Okay. So you put all of them in the same matrix. So this is first function that you need to know. And then you need to define name of the distance. The default, if you do not give any name, is Euclidean distance. But you have many other distances, like here. You have that list of different names for distance on the right side, okay? So you have Minkowski distance, you have Mahalanobis distance, Euclidean distances, standardized Euclidean distances, all kind of Spearman, correlation, cosine, Chebyshev, whatever. You have tons of different distances. Okay, you can find with help of MATLAB, you can find definitions for each one of them. All right, what they mean. But we talked about a few of them, like Euclidean, Minkowski, city block, which is Manhattan distance. Remember this kind of city block movements. So you have a few of them be learned, some of them we haven't learned. You have more, obviously. And you can define even your own distance if you want to, your own function, which would be computing distance between two different vectors. And this one is computing pairwise distances, and the order it returns vector. And this vector will include these distances between vector 2 to vector 1, vector 3 to vector 1, vector m to vector 1, and then 3 to 2, 4 to 2, 5 to 2, and so on. So it will give you a long list of these distances, okay? But it's not very convenient to represent it, right? Because, you know, it's like how you find specific distances between A and B, like channel 5 to channel 6, like which number it should be. It's not very convenient. I mean, you can count, right? And you probably have some formula to find that particular value, that this one will be maybe between channel 6 to 7 and whatever. But I don't know, like by looking at these coordinates, I cannot tell you, right? You just need to count how many you have in each column. But what this coordinates giving you is that lower triangle, okay, lower triangular matrix. So you can put them here as a lower triangle in that matrix below the main diagonal, because main diagonal is always 0 by definition. The distance between vector and itself, if you remember, we define distance as 0. It has to be 0, right? Remember that part? That if you take in vector and distance to itself is by definition 0. This is how distance is defined in the first place. That's part of the definition. The distance to itself is 0. Okay, so all of the main diagonal, you don't need these numbers. And this is why this vector does not include 1 to 1, because it's known to be 0. 2 to 2 is also 0. 3 to 3 is 0, and so on. So what happens is when you planting all of these numbers as columns here, you get entire matrix. But you don't need to do that by hand. You have for that function which is called square form. So square form takes that distances vector and converts it into that matrix of these pairwise distances. So on the x-axis, you have like input, like first vector number, and on the second one, you have second vector number. So it's like this number is between vector 1 and vector 1. This is between vector 2 and vector 1. And obviously, this matrix is symmetrical, which means it's same values on the, if you flip on the main diagonal. Okay, the transpose of that matrix equals to the matrix itself. Because distance between, again, by definition of distances, the distance between vector 5 to vector 7 is same as distance from 7 to 5. So it doesn't matter the order in which you compute the distances, okay? All distances are like that, satisfying that rule. So image SC will give you colorful representation of the image of that matrix, okay? And this is color bar, which will tell you what are the values and how colors, what numbers colors are coding in that type of matrix, okay? So for example, clearly you can see that 0 is dark blue, and all of the main diagonal are zeros by definition again. But some vectors are more correlated than others. For example, vector 1 is correlated very poorly, not correlated, but the distance, Euclidean distance in that case, to almost all of the vectors is horrible. So vector 1 is very different from everything else. But for example, vector 3 and 4 are very similar. You see this value, dark blue, it's very close to 0. So channel 3 and channel 4 in my recordings have very low Euclidean distance compared to other pairwise distances, okay? And some others also very close, like 8 is close to 6. So this could be because of the geometry or where they were recorded actually, or could be because you have some interconnection between different parts of the brain through some neural bunches of nerves which are connecting different points in the brain, and you have good communication between these two centers. So everything which is dark blue is well connected. Everything which is bright yellow is not connected, okay? This is how you interpret it. So you can see that some of the channels are much worse connected to others, and you can build practically connectivity map of some kind here. So this is different distance. So this Minkowski distance for p equals 5, or you can use any other number, whatever it is. Looks similar to that one, but not exactly the same. It's kind of more dark, I would say, a little bit, maybe. A little bit different, okay? And again, Minkowski could mimic exactly the same thing. So if p will be 2, you'll get exactly the same matrix, because it's Euclidean distance. If p equals 1, then you get L1 distance, which is sum of absolute values distance. So what is the intuitive difference between these distances if you're thinking about values for signals that you would say? So Euclidean distance is sum of squares and then square root of that, right? So you're practically emphasizing bigger distances, because square of big number is much stronger than square of small number, right? So like 1 square is 1, but 5 square is 25. It's 5 times bigger. So bigger the difference is, more you emphasize it in Euclidean distance. In absolute distances, all of the distances are equally emphasized in the distance, okay? So they have same value. So if you're thinking about error, for example, and you want to emphasize outliers, you would rather use Euclidean distance. But if you don't want to emphasize outliers, then use L1 distance, which is city block distance, because it's not taking into account like how big your error is. It will always be proportional to the error and not proportional to the square of the error, all right, in the distance computation. So these are the intuitive considerations, what distance to choose for different things, all right? And Minkowski goes on that entire spectrum from L1 to infinity, L infinity, okay? So L infinity means that you're taking only maximum and you don't even care about the second dimension. Like what is the closest dimension that you pick? And this ignores all of the other dimensions, which is, well, sometimes great for simplicity of computation, but in many cases it's not great for whatever you need. It's like biggest distance between the signals. What is the biggest difference between the signals? Is it informative? No, it will be based, most likely based on 1 point only out of the entire signal in time, right? So it will not give you like great information about your signal. Though if you care only about like what is the worst case scenario between the signals, then this is the norm that you need to use. This is the distance that you need to use, maximum distance. If you are looking only for worst case point, like where is the worst case, all right? Another example, for connectivity studies, people typically do not use distances in general. They use correlation between channels, because higher the correlation is, more it is connected. So it's more intuitive, I would say, in terms of interpretation of it. And also correlation is typically normalized between -1 and 1. But PDIST will give you only distances. It will not give you correlation, right? But they have something which they call correlation distance. It's not correlation, it's still distance, okay? But here how that thing is computed. So that distance correlation is computed as 1 minus, practically speaking, that entire thing is Pearson coefficient, all right? So it's minus the correlation. So distance is 1 minus correlation. And this distance will be obviously between 0 and 2. because correlation is between -1 and 1. So if you're taking 1 minus something in the range from -1 to 1, you get numbers from 0 to 2. And this is what you see here. So this correlation distance is distributed up to 1.7 probably, or something like that. And these are the numbers. Again, similar to previous distances, these are very well distanced, very close to each other. But this one is not as yellow as it was before, you see? So it's kind of different. It shows you different things about these channels. And for example, this was almost all yellow, and now this one is pretty blue compared to the previous one. So it gives you additional information about the things. But how do you compute correlations that people in neuroengineering actually using? You're just making that 1 minus distance. This is, you kind of putting it back to Pearson coefficient. And then you get correlation, which is like very yellow, practically almost 1 when it's very well correlated, and very blue when it's not well correlated, like low correlation coefficient. All right, so if you more used to statistics and how to interpret coefficients, you just do 1 minus distance, you will get it back. All right. Any questions? Okay, so that's it for this lecture.